Welcome to Finite Element Methods. Today we'll be discussing an exciting way of solving transient analyses by decoupling the mass matrix, the stiffness matrix, and coming up with an approach of just solving a bunch of mass and springs in a very simple way. And this is a very exciting moment because if you were to look at the transient analysis I had discussed 2 lectures ago, you could see how computationally expensive it could be. We had to really solve, say you have a million degrees of freedom system, we have to solve those that large system over time, and that can be quite computationally expensive. But what I want to explain is this fundamental idea of mode shapes. The mode shapes helped us understand how the system behaves dynamically. It describes the fundamental dynamic characteristics of a particular structural system. But these mode shapes, we're going to use them. We're going to use them to simplify the problem. And they're essential in this idea of modal transient solution. In other words, I have million degrees of freedom system, but I'm going to simplify the problem by just considering the mode shapes and saying that, hey, the structural response of the system depends on these mode shapes. So in the modal transient solution, we'll use the mode shapes to determine the response of the system as these define the dynamic characteristics of the system. So what we're saying is that the mode shapes are the pillars, they're the foundation of how the structures deform. So if I can determine what those fundamental motions are, then I can perhaps linearly superimpose them by superposition, and then determine the dynamic behavior of the system when laws are applied. In the previous lecture, I discussed how we can determine these mode shapes and frequencies. And we're going to use that approach moving forward in this analysis that we'll be performing next, which is our goal is to determine the transient behavior of a system over time. Again, computationally expensive, as discussed 2 lectures ago. I have millions of degrees of freedom system, very difficult to solve in terms of computational time. But if I can simplify the problem, why not? In the example I showed in the previous lecture, we showed that the mode shape for the beam, when we analyzed with 20 elements, so 20 beam elements, we had 40 degrees of freedom system. And so therefore we should expect 40 mode shapes and 40 eigenfrequencies for that beam that we studied. But not all mode shapes are known from the frequency analysis. I mean, that's something that we should be aware of. So let's look at what is going on, right? So if I say that the deflections as a function of time in a linear system is equal to a linear combination of mode shapes, that'll be very powerful. So say I have this mode shape from the previous lecture for a beam that's clamped. That's what you'll expect for the first mode shape. For the second mode shape, this is what I got. For the third mode shape, this is what I got. I have like 40 of them for this beam with 20 elements. So if I call these shapes, I know the shapes because I know the nodal coefficients. So remember, these are the nodal values, phi1, phi2, phi3, and so forth. This right here represents the vector that contained the nodal values, right? Which were the deflections and slope for ordered Bernoulli beam. So I know how to calculate the mode shapes per the previous lecture, how to calculate the frequencies and mode shapes. I know how to do this for a system. So what if I told you that the deflection of the system for a linear system is going to be just a little bit of phi1, a little bit of phi2, a little bit of phi3, and so forth. Now, remember the mode shapes were of arbitrary amplitude. From the previous lecture, we showed how that was an eigenvalue problem. So the mode shapes are arbitrary. As a consequence, phi1, phi2, phi3 can be any amplitude. And so what if I multiply each phi1 by a corresponding amplitude that's unknown? Phi2 times an amplitude that is unknown. Phi1 and phi2, phi3, these are all known values. It's just that we can scale it to whatever number we want since they're arbitrary in terms of scaling. Is the amplitude that's uh, arbitrary, not the relative values with respect to each other. So obviously, because you can see there's a shape here being shown, so it's going to maintain that shape. The question is how much more amplified it is compared to what I'm showing here. So we're going to put this factor on top of phi1, a2 times phi2, a3 times phi3. For example, say that there's a particular motion for which this mode shape does not show up, then a3 will be 0 for that case. So what we're going to say is that the only unknowns are these a1, a2, a3, and so forth. Um, so what I'm going to say is that the deflection of the system of the beam that's clamped when a forcing function is applied to that system is such that it's a linear combination of these mode shapes. Now, note these mode shapes do not depend in time. They're independent of time. They're fully known. We know each of these vectors. I showed you how to do that in the previous lecture. So the only unknown is these amplitudes, and they depend on time. That's the only thing that could depend on time. So what if I put these phis into this bold, phi bold? So these vectors are put in here. So this becomes an m bold, um, m bold times m bold. So I have here a vector of mode shapes. And this a1, a2, an go into this vector of uh, unknown amplitudes. Phi bold is fully known. It's a matrix. It's a square matrix, actually. But say I have a system that has, say I model this beam with 1,000,000 degrees of freedom. Anytime I apply a forcing function, maybe not all the modes participate in the motion. Perhaps it's going to be maybe the top first 10. In fact, the more complex the mode shape, the less likely it's going to really take that shape in real life. So what I could say is, hey, what if I truncate? I don't use all the modes to determine the deflection of that beam. Okay. Um, that could be a perfectly good assumption. Depends on how you go about that. Say you have a rocket or an airplane that has millions of degrees of freedom. Not all millions of degrees of freedom are going to contribute to the motion when a forcing function is applied. So you can make an assumption that maybe not all modes participate. And I'll truncate it. I say, okay, I think all the modes up to phi3 are the ones that matter. Maybe I want to stop there and then delete the rest of them and just say that the deflection of that beam depends on these first top 3 modes. In the beam example, I had 40 modes. I could say the first 3 are the ones that matter. And so I could truncate um, how many of these modes I want to add up to get this total deflection of that beam. So how do I determine where to truncate? Typically, the frequency content of the forcing frequency could be used to determine what modes can be truncated. So the frequency content, if the forcing function has a frequency content up to 1,000 hertz, then modes up to 1,000 hertz should be included in the dynamic transient solution. So that's one guidance. You can go even a little bit higher than 1,000 hertz just to be safe. So I could truncate. I don't have to use all the modes. And that's very powerful. Say I have a rocket that has over millions of degrees of freedom. So I have millions of eigenvalues and mode shapes. And if I have to use all of them to describe the motion of that rocket, that's computationally expensive. But what if I told you that perhaps I want to worry about mode shapes below 150 hertz? That'll truncate the number of modes I have to consider, and that'll make this problem a lot more tractable. Maybe below 150 hertz, I only have 30 eigenfrequencies and mode shapes to worry about. Well, I've simplified now the problem into 30 degrees of freedom because I only have A1 through A30, 30 of these things that I don't know. And so I've simplified the problem from million degrees of freedom system to just not knowing 30 of these amplitudes. Again, say I have a rocket with million degrees of freedom system, and then that will result in million of eigenvalues and eigenfrequencies. That means that it'll be very computationally expensive if I had to find all the A's They have to be multiplied by phi's, right, if I have millions of them. But what if I told you that maybe the first 10 A's matter? These first 10 frequencies are the ones that matter, mode shapes. Then I simplify the problem in just finding 10 of them, 10 of these A's. So very, very powerful idea if I can get there. So what if I truncate the space, the solution? I'm going to truncate. I'm going to say, instead of considering all n degrees of freedom, I'm going to consider just R of them. So I'm going to truncate the number of mode shapes to just R. So I'm going to truncate it. Out of a million, I'll consider 10. So this becomes a million times 10 in terms of the size of phi bold. And A bold becomes just 10 of them that I don't know. Uh, a lot better than having million degrees of freedom here, million times million, and the number of degrees of freedom not known becomes a million in A bold. But if I truncate it, A, which are the unknowns, becomes a lot smaller, and that's very tractable. I'm putting the size of the matrices here so you can see what's going on. Because phi bold is going to be a column vector of n rows. The only thing I'm changing is how many of these mode shapes I'm going to use. If I use R of them, which is a subset of all the ones I have, the millions of the ones I have, then this becomes not a square matrix, becomes n times R. And A bold is R by 1 because I'm only considering just maybe 10 of these A's. So R is 10 in that example, right? So an example of the beam, actually, if I were to consider 3 mode shapes, then R is 3. So I only have 3 unknowns. And N is 40 per the previous beam example with the 20 elements, because each node had 2 degrees of freedom. So I have 40 eigenfrequencies and 40 mode shapes. So you can see here, I've simplified the problem quite a bit in that hypothetical example. I showed you already, and we've already demonstrated that the equations of motion after a finite element discretization, we did this 2 lectures ago in lecture 14, and we showed how we can discretize the system by using finite elements, using shape functions, and then we end up with this equation of motion that you see here. Okay, so if I have millions of degrees of freedom, then M bold becomes millions times million. So these are square matrices basically, and this could be computationally expensive to integrate over time. And depending upon the numerical scheme, you may have to invert the matrix even. So that is computationally expensive, and you have to keep track of that. It's not, it's not easy. Um, it requires some amount of work. So if I assume the total dynamic response is a linear combination of mode shapes with unknown amplitudes. So I know the phi bolds because I know how to get the mode shapes. The only thing I don't know is these coefficients that are unknown. Then I have phi bold times A bold. And notice I'm just selecting R of them, like I said before, a truncated set of mode shapes. So what I'll do is then substitute into this equation here. D bold will be substituted here with phi bold times A bold. Now phi bold, like I said before, does not depend on X, does not depend on time. These are just numbers. So when I take this derivative, since the only thing that do not depend on depends on time is A1, A2, and so forth, that's the only thing that has the A double dot. Phi bold and M bold are fully known. C bold and phi bold. C bold is a damping matrix. I'll discuss more about that. And so this D bold dot becomes A bold dot. And this right here becomes just K times phi bold times A bold equals Q bold. Now notice that here, M bold is a M by N, right? It's pretty big. It's a million degrees of freedom by million degrees of freedom for a rocket that has that many degrees of freedom. Phi bold is a M by R. So this is not very convenient. So what if we pre-multiply by the transpose of this mode-shape matrix. If I do that, what I get here is, and I will do it everywhere here, what I get here is R by N, this M by N now, and this M by R, and this becomes a square matrix by doing that operation. What I really get here is R equations now, which is actually very convenient and very powerful. Here, I had N equations, but by multiplying by that transpose, I turned the problem into R equations. So here I have millions of degrees, millions of equations, and I then turn the problem into a subset of equations. A very powerful idea that simplified the problem even further. And if we have R equations, right, which is a reduced set from the N equations we had. So say I have a rocket, million degrees of freedom system. I've simplified the problem into just having maybe 10 equations, right? Which is extremely powerful. Think about it. It's a mathematical miracle. So for the beam example, return to that for a second. Just again, 40 mode shapes for 20 elements. If we have determined that the first two mode shapes are the only ones that matter, and we truncated the mode shapes just to 2, then the number of equations reduces to 2. I just get 2 equations instead of 40. Obviously, that will introduce error because I'm not using all the modes. I'm using a subset. So this can be addressed by using residual modes, which is not discussed in this course, but I recommend you look into that. So there's a mathematical miracle that actually happens when I do this pre-multiplication. And I'm not going to do the proof here. I'm not going to prove it. But the mass matrix and stiffness matrix fully couple all the degrees of freedom system. However, this operation here, if you look at this is fully coupled. But by doing these operations, what you find is that when I do this multiplication, it will result in R equations that are fully decoupled, which, I mean, that's an insane mathematical miracle. And that's because there's a property that has to do with orthogonality of the mode shapes with respect to mass and stiffness. Here, we assume that the damping matrix is such that it will decouple it. I'll discuss more of that. But what is the powerful thing, and it can be proven, and I won't prove it in this course, but if I took phi off diagonal terms and multiply them in this multiplication, it will get 0. Same with the stiffness matrix. So you'll just get a bunch of diagonal terms, which is very powerful. So these equations here will turn into R decoupled modal equations, which is incredible. It's a bunch of mass and springs. We turned a fully coupled finite element model with millions of degrees of freedom system, with millions of eigenvalues and corresponding mode shapes. And I want to figure out how the aircraft deforms due to forcing functions applied to it, maybe from aerodynamic loads. But I maybe say, okay, out of all the mode shapes, maybe 25 matter. And I simplified it by saying, okay, I'll pre-multiply by phi bold transpose, and that'll turn my million degrees of freedom equations into maybe just 25 equations. But further, this multiplication turns every single one of these into a diagonal matrix, which means that I have 25 decoupled equations. And that's powerful. Very, very powerful. Notice how Q bold here is a function, and that's a forcing function here. And so this multiplication just gives you a QIT, which, you know, that's what's changing over time. Another important consideration is that KI divided by MI actually happens to be the frequencies of the system, omega I squared. So not only we can actually, we know what the eigenfrequencies are. So I know what this is. So how do I deal with the damped system? How do I deal with this CI? One approach is that for the ith frequency, CI, you make CI equal to 2 CI omega I MI. I know MI, I know omega I. MCI is the damping ratio that can be measured. And if it's not available, you can assume 1% as a starting point. But again, this is a set of, so if I know this, I know this, I know this, I know CI. And so this is a set of uncoupled second order differential equations, which can be solved using the Newmark beta method. You can actually use Newmark beta method, or you can actually find a way of time marching a solution some other way. But now it's uncoupled. So that should be very doable to use Newmark beta method in a systematic way. So once you solve for using the Newmark beta method, you solve for A as a function of time. You can plug it back in here. And what that gives you is the total deflection of the system as a function of time. You can reconstruct the actual deflections because these are mode shapes multiplied by the corresponding amplitudes. I found that using the Newmark beta method by solving this equation here. And that gave me the deflections for the beam as a function of time, or the rocket or the airplane, which I've been using as examples. It is important to consider the boundary conditions. So we have to discuss that because you have to come up with the initial boundary conditions for the system. So we have this first equation right here. So just keep that in mind. So we know that this equation is completely true. So I'm going to do a little trick. I'm going to pre-multiply this equation by a particular mode shape that I will select times m bold. So I'll select one of them times m bold, and I'll pre-multiply throughout all these equations. And this could be mode shape number 1, 2, 3, 4, 5, whatever. Let's assume S is 1. If I do that, phi 1 times m bold times phi 1 is the only thing that will survive, because phi 1 bold times m bold times phi 2 is 0 due to the orthogonality properties I discussed right here. If I and j are not equal, this is 0. So the only one that's going to survive is when s is equal to 1 or s equals to 2. So that's the one that's going to survive. So that's what's going on there. So due to the orthogonality conditions of the motion with respect to mass, what you find is that when I do this pre-multiplication, on the right-hand side, the only one that will survive is when this phi bold is s, right? And that's AST right there. So then I can calculate AS of t like that by solving it for like that. And this is what I get. So A dot of t as a function of time, we'll have a dot here, for example. So we can use this information to determine the initial conditions for the Newmark beta method, because you know the initial conditions for the problem. And you know this fully for mode shape S, you know the mass matrix, and then you know the initial conditions of the problem, what the deflections are initially, and what the velocities are initially. So you can calculate what these two are to time march this solution here, which is required by Newmark beta method. And this you can be calculated for S all the way through R. So I want to talk more about damping. The system exhibits energy loss that's attributed to material nonlinearity, and that can be due to internal material friction or external friction. And that will prevent large amplification at or near resonant frequencies. That's typically the case. It's sometimes really difficult to fully characterize the source of damping. Mechanical dampers can be added to introduce damping to the system. So that's very important. That's typically done. But two approaches are used to make C bold diagonal, the damping matrix here, diagonal. Okay. I want to talk more about that. You can specify the damping ratio at each frequency. So you can measure from test and apply it directly to the C matrix and make all the off diagonal terms of 0. So you can specify a damping ratio, this damping ratio for each of the frequencies, and not worry about the coupling that could occur here. So you can directly do that there, calculate those C's. The method two is called proportional viscous damping. The proportional viscous damping assumes that the damping matrix is proportional to the mass matrix and stiffness matrix. Here, A is the proportional mass damping, and this here is the stiffness proportional damping. So A and B are parameters we're going to try to find. So that's how you could incorporate damping, is by using this formula. By doing this, we're already assuring that the following quantities are diagonal and can be determined. Why? Because let's look at this. So when I have, this is what I did in this operation, right? We did this operation here. But by making C bold proportional to M bold and K bold, if I did that operation, I'm doing it for each of these also. But I already showed you that this becomes diagonal, and so it works out nicely, and I get AMI plus BKI. In other words, I'm able to find what CI is in terms of AMI and KI. In my book, I have an example worked out on how this works. You can see here that I can solve, I can basically, I know what AMI is, which is this right here, in terms of damping ratio. And I know KI in terms of omega I squared, which is this equation right here. I already discussed these two equations previously. I encourage you to go back in the video and watch it. Um, I can further expand this more. So MI shows up again. So I can plug in this whole thing there. And when I do, everything simplifies to the simple equation here. CI equals all this here. So if the damping is known at two different frequencies, if I know the damping at two different frequencies, then I have two equations and I can solve for A and B. So if I know omega 1, for example, I know the damping at omega 1, and I know the damping at omega 2, I can solve a linear system of equations to calculate A and B. Generally speaking, this last approach, which is called also the mass proportional Rayleigh damping, damps the lower frequencies, and the stiffness proportional Rayleigh damping damps the higher frequencies. So it has been demonstrated that this can be conducive to non-physical issues that arise with this formulation. And as a consequence, I point you to this particular paper to kind of read the issues with proportional damping. However, it has been used quite extensively. And so I don't want to say that don't use it, but keep these things into consideration. The better approach is to directly measure it and then just plug it in directly into this equation, in the uncoupled equation. So what is the analysis process flow you have to find? So what is that you need to do? Develop the finite element formulation for one element using the partial differential equation, equations of motion, of course. Assemble the system and impose the essential boundary conditions. You then determine the mode shapes and frequencies of the system for the free vibration problem. So no forces applied, just boundary conditions. That'll give you the frequencies and mode shapes. That's what I discussed in the previous lecture. The total deflection of the system is assumed to be then a linear combination of these modes. So we'll use a truncated set of mode shapes in the transient simulations. We'll then develop the uncoupled system of equations in the modal coordinate and impose the initial boundary conditions and solve this using the numeric beta method. Once the solution is obtained, you can then recover the deflections of the system as a function of time. And I discussed that here carefully. So once I know A as a function of time by integrating these equations, I can plug it in here because I know the mode shapes. I can calculate uh, the deflection, the actual deflections, as a linear combination of these mode shapes. So just to remind you one more time, we can use the numeric beta method, but we can expand this for damping because previously I did not discuss how to deal with damping, but it's the same thing. You have this equation here, this approximation for U bold. which depends on the velocity and depends on acceleration. And the beta here is a value that you prescribe based upon which which time integration procedure we want to use. This was discussed uh, in lecture number 14. I discussed this, how to deal with this. The velocity can be approximated using Taylor series expansion as well. But now you can actually use this directly here because now I have damping included. You can also include this into this equation, and then you get this equation here. You can then further progress this further. So u dot can be plugging all this in there, right? And then for u, you can plug this whole thing there. And then solve for u double dot. So the acceleration the very next time step. Now notice I know in bold, I know the delta t, beta 1, which is the what beta method I'm using. C bold, the damping coefficient matrix. 1/2, I know delta t, I know beta 2. Notice how beta 2 shows up now. And K bold. I know all this. I know all this stuff on the right hand side. So I can then solve for acceleration, which means I have to invert this and do that work, right? But we have uncoupled, I mean, this is the mathematical miracle here, right? We have uncoupled the equations of motions. And instead of having to solve n fully coupled equations, we're now solving small number equations. We looked at reducing the number of modes using analysis by using a truncated set. And we did that by examining the frequency content of the forcing functions and making some smart decisions. Now, let me summarize it one more time. So I have medium degrees of freedom for an aircraft. I'm going to use maybe, say, 20 of those modes. What I'm basically telling you is instead of solving those medium degrees of freedom, I can just solve the equations using 20 of them, perhaps. And they're uncoupled too. So, what a powerful idea, right? What a powerful idea. And there's some errors introduced, and it works for linear systems, but it's still very powerful. How will you do this in Abacus? So, in Abacus, you'll have a restart read that's going to read the frequencies and mode shift from the previous analysis. And we'll illustrate that in some examples in YouTube. You have the amplitude where you're going to provide the loading environment as a function of time, and that'll be called out here. Here, you're going to call out the modal transient analysis procedure. Here, what we're saying is that we're going to go in time steps of 0.0001 up to 0.2 seconds. And here, I'm going to select particular mode shapes. I'm not selecting 40, I'm selecting 10 out of the 40. And I'm going to apply a damping of 0.01 for mode shapes 1 through 10. So 1% damping. And I just run the analysis. I have to call a restart file, so it calls out the mode shapes and frequencies. So it will read them, right? And in the previous video, if you watch carefully, I had a statement that's necessary for this analysis to run. So in this example, I'm showing a cantilever beam that I have previously discussed and showing how you could basically run the model. And then you can look at the mode, the mid-node deflection and tip deflection. And when you compare against what I've shown couple in the lecture 14, you will get the same answer. So, but much more efficiently. Let me go to an application here really quickly. So mode shapes and frequencies. One application that's typically really studied is spacecraft finite elements. They can have over thousands of degrees of freedom. The fundamental mode shapes and corresponding frequencies can be determined typically below 100 hertz. You can find those mode shapes and frequencies very nicely. And you want to verify that model. So one thing you can do is to calculate the dynamics, the eigenfrequencies, mode shapes, and then go from there, right? So you can go from there. Now you can instrument the spacecraft and put accelerometers and things like that, and you can then compare how the mode shapes and frequencies of the model compare to the testing. We already discussed that we need these mode shapes and frequencies to be able to drive a transient solution and really understand how things are behaving. So again, instead of solving millions of degrees of freedom system of a huge spacecraft model, if I can figure out a way of using a truncated set of modes, why not, right? And that's and uncoupled too, right? I invite you to look at this paper here on the bottom right. It discusses how you could do these model correlations between finite elements and testing. So model testing allows identification of the natural frequencies and mode shapes. You can basically determine by perturbing the structure through testing, you can determine the mode shapes and frequencies. So dedicated model test equipment is used to disturb the structure into motion. That's called wrapping. And then you will record the distribution of the motions throughout the structure. The end results of a model test are the various natural frequencies, mode shapes, and impedance data of the structure. These data are identified from digitized input signals using efficient curve fitting routines. Recall that theoretically, mode shapes are orthogonal to the mass matrix and the stiffness matrix. Remember that. So we're going to use that fact to really compare finite elements to testing. Let me show you how. So the finite element model is acceptable for modal transient analysis if the finite element compares well to modal test data. If it doesn't, then your finite element model requires to be fixed. If it's not matching test data, there's a problem with the finite element model, and you're going to probably produce results that are nonsense. There's a model analysis of a turbine generator foundation. As an example here at the bottom right, they use accelerometers and they put them at these points that you see here. They use 68 nodal sites, and they also perform finite elements. So that's an interesting paper that was taken from here at the bottom. The model response from finite element is compared to the model response from testing using the following approach. I have this equation here. Now, what I'll do is the mode shape will go here for the finite element, and the mode shape from the test goes here because I can calculate what the shapes were from the test. I know the shapes from the finite element model, so I can then calculate this. And now, if the test and finite elements were the same, then I can plug in phi bold FEM here, and I should get a diagonal mass matrix, right? But in reality, there'll be an error between the finite element and test, and so therefore this will not be fully diagonal. If this calculation result in a fully diagonal mass matrix, then we can say that finite element compares well with the mode shapes measured in test. This is called the cross orthogonality check. Here you can see that in this case, the calculated and measured frequencies were agreement. Now you don't see the mode shapes being checked, but that was checked. You can see here the measured frequency, the calculated frequency is not too bad across the board. You also want to check the mode shapes, right? We'll talk about that. So the you want to do this check, the cross orthogonality check. So you take the mode shapes of the finite model. You can determine the mode shapes from the test because you instrumented it and you disturbed it, so you can determine what are the mode shapes there. This multiplication should give you a diagonal if it's perfect. If you have an FEM model that's perfect, but that's never going to happen. So in perfect reduction, the diagonal values of orthogonality and the cross orthogonality matrices have the value of unity, and the off diagonal terms will have a value of 0. If you had the mode shapes mass normalized, since the mode shape is of arbitrary amplitude, we can scale the mode shape so you get this. Okay, so that's one way to normalize the mode shapes. But remember, the mode shapes can be arbitrary. So if I have a way of making it so that this multiplication gives me 1 across the diagonals. Usually, good correlation is one where the eigenfrequencies between test and analysis are within 5%, and diagonal terms are greater than 0.9. but the off diagonal terms are less than zero point 0.1. It depends on the program. Here's an example that was taken from this paper here at the bottom that shows how you could compare test and analysis. You can see here the test here in the first two columns, final elements in the second two columns. You can see how the frequencies are being compared across, and it did fairly well, except for one of the mode shapes here, 6% off. And you can see here how they're checking the off diagonal terms across the board to see how well the analysis did. You can see there's some pollution let on, not very good above 60 hertz, a lot of issues there. But for the most part, not bad. And this shows that how how you can use a modal analysis and how you can instrument the test to then compare both to see if they match well. And this is a mathematical miracle by itself. So a lot of mathematical miracles here, right? Because in lecture 14, we talked about having to solve a problem by integrating over the domain for a fairly large system potentially. But in this lecture, I'm teaching you that you can use the modal frequencies and the eigenfrequencies and mode shapes to really simplify the problem a lot more. It's an approximation, of course, and it only works for linear systems or close to linear systems. And it can be a very powerful tool to solve transient problems in a very effective manner. So, with that said, I thank you for listening to this lecture and you have a great day.